Okay, everyone. So today we have a chance to review all of our lessons that we covered in Unit 1. That's lessons 1 through 4. So let me start by asking, does anybody have any questions, any areas that they feel like we need to cover again or go over, explain a little bit more in detail, review some more?
I think it was lesson 3. I completely don't remember well, but there was one.
Okay, let's go to lesson 3. So lesson 3, chemical bonding. Okay, so chemical bonding, we talked about the octet rule. We talked about Lewis structures. So let me know where it was that you think you needed some more help, or which slide in particular, or which area. We talked a little bit about Lewis structures. We talked about the idea of valence electrons, how to draw Lewis structures, how Lewis structures and quantum mechanics were related. There were some support questions that I hope everyone got a chance to try. Then we talked about intramolecular bonds, bonds that are within molecules. The 3 different types of bonds, excuse me, ionic covalent and polar covalent bonds. We talked a little bit about electronegativity on the periodic table and the elements that are which ones are most electronegative. We talked about the difference between electronegativities between 2 atoms that are in a bond, that are bound to each other. We talked about predicting bond type using electronegativity and the delta, the change, the difference rather in electronegativity between 2 atoms in a bond. Then we covered ionic bonding. Then we talked about Lewis structures for polyatomic ions. So Borna, let me know if I'm in an area that you feel like that was the part that I need to go over again. Covalent bonding. Then we started to talk about valence bond theory. And that went through, we spent a few slides talking about valence bond theory.
Yeah.
Okay, so is this where things started to get a bit confusing maybe?
Yeah, basically.
Yeah, okay. All right, so valence bond theory. So we can go over this again. Does anybody else feel like this is a good area to review? Judy and Sasan, how did you feel about valence bond theory?
Yeah, I think this is a good one.
Okay, all right, so let's talk about valence bond theory again. So valence bond theory explores why and how electrons are shared between atoms that are in a bond together, and how each atom, each with its own orbitals and electrons, contributes to the formation of the covalent bond with another atom. So the covalent bond between 2 atoms is formed when a pair of electrons is shared. This is a very important concept to remember in a covalent bond. The 2 atoms don't donate ions to each other as is in an ionic bond, but they one doesn't donate and one doesn't receive, but rather it's a sharing. So a bond is formed by the sharing and by the overlapping of their orbitals. And that is a state where a lowest energy is obtained because the electrons are shared in a way that allows each atom to experience that stable octet outer orbital and to form a new orbital with a pair of opposite spin electrons to stabilize itself. So there are some key points in valence bond theory. And first one is that a half-filled orbital in one atom can overlap with another half-filled orbital of another atom, and by doing so, they form a new bonding orbital. And the new bonding orbital consists of 2 electrons, and these electrons, as we know from quantum theory, must of course have opposite spins. And when the atoms bond, they arrange in such a way that they have maximum overlap. And then from this, we will talk about some of these ideas in Vesper theory, where Vesper theory assumes that the majority of the electron density of the bonded pairs of electrons is actually close to the bond itself, to where you would have the 2 atoms bond together. And then valence bond theory explains why we can make this assumption. Just one moment, please, while I admit Shadissa. Okay, so let's continue a little bit more with valence bond theory. Okay, so so far, do we understand that valence bond theory it talks about the idea of the sharing of electrons in a covalent bond to form
Yes.
a new bonding orbital?
Yeah.
Okay, let's highlight this one because I think this is an important term here. All right, so then we went to explore the idea of just a very basic, very simple situation where you have 2 hydrogen atoms in a bond. So the electrons of each of these 2 hydrogen atoms, as you recall, is in the 1s orbital, okay? And is everybody clear about that, about the hydrogen atom having electrons in the 1s orbital? Borna? Or Judy or Sasan or Shadisa, is everybody clear about that? Does everybody remember back when we were talking about orbitals and the way electrons fill out orbitals? Does everybody remember that hydrogen has 1 electron and that resides in the 1s orbital? Is there any is everybody clear on that?
Yes.
Yes, okay.
Yeah.
Yeah, Borna, okay. How about Shadissa and Judy? How do you guys feel about that? You guys are clear on the idea of how on electrons in orbitals for different atoms?
Yes.
Yeah, okay.
And so, if you have time, can you explain one more time?
Okay, so the electrons in hydrogen has 1 proton, if you recall. It's element number 1 on the periodic table. Its atomic number is 1. That means it has 1 proton, and as such, it has 1 electron. And this 1 electron is in the lowest energy state. So let's just take before we continue any further with valence bond theory, and I will come back to this, Borna, let's just make sure everybody's clear on where are these 1s, 2p electrons coming from. So let's just go back a bit. And I think it was here in this lesson that we talked a little bit about these different, so okay, let's talk about it right here. Okay, so if you recall, we talked about the 4 quantum numbers that were important in describing the electrons and the state of these electrons in each atom. And the 4 quantum numbers were N, the principal quantum number, L, the secondary quantum number, and then there was these ML and MS, the 3rd and the 4th quantum number.
Miss, I remember this from grade 11, but could you go over what each of them mean again?
Yes, okay, so let's go over that again. Let's go over the 4 quantum numbers again. Okay, so if you recall, we talked a little bit about how in the Bohr model, where the electrons were described as being in shells, that's actually not entirely a correct way of depicting them. Rather, each of these electrons isn't described by, each of these sets of electrons isn't described by one principal quantum number relating to which shell number 1, shell number 2, shell number 3, shell number 4. Rather, there's 4 quantum numbers that describe these electrons. And if you recall, Heisenberg came up with the idea that it was impossible to know exactly both the position and the speed of the electron. And so the idea of trying to actually locate an exact location for the electron was abandoned for the idea of rather coming up with a probability distribution for where this electron was going to be found, so that electrons don't actually orbit the nucleus in a fixed radius. Rather, there is a probability distribution that they are somewhere in this electron cloud, let's say. So this is how the Bohr model kind of evolved into the quantum mechanical model, whereas there's different orbitals, and each of these orbitals have their own unique set of quantum numbers. The electrons that occupy each of these orbitals have their own set of unique quantum number, and that each electron is described by the set of 4 numbers. And these orbitals are regions where electrons are most likely to be found. Now, these 3 numbers were N, L, M subscript L, and MS. So N is the principal quantum number. That's what the Bohr theory established. It actually described the principal quantum number N. And N can have values of 1, 2, 3, and so on, and it increases as the orbitals become larger. Yes, Barna?
So it's basically each ring outside of the nucleus.
So actually, we're gonna stop really thinking about them as rings and think about them as orbitals and energy states. So that when N is equal to 1, when the principal quantum number is equal to 1, there is, this is the first energy level, and it has only one type of orbital in it. So when N is equal to 1, it only has one kind of orbital in it. When N is equal to 2 at this energy level, there's 2 kinds of orbitals, and it has this kind of orbital, an s orbital or a p orbital. And this s and p designations come from the values of L, so the secondary quantum number. So we said that when L is equal to 0, let me find that slide where we talked a little bit about this. Yeah, right here. So that was the first principal quantum number. And the L is the secondary quantum number, and it can have values from 0 to n-1. So that the values of L, for example, can be anywhere between 0, 1, 2, 3. And it just became easier to designate, instead of these numbers, to designate them with letters, so that then you can talk about a quantum number N, and instead of saying N1 L0, you can say it's in 1 S, and that way you know you're talking about N is equal to 1 and S is and L is equal to 0 when you're talking about 1S. Or when you're talking about N is equal to 2, then that relates to that under the second energy level. You could have L values of 0 and 1. And 0 and 1 in the L value corresponds to S and P letters that are used to describe these subshells. And these would be called then 2S and 2P. The 2 relates to the N is equal to 2, and then the S has to do with the L is equal to 0, and the P has to do with L is equal to 1. And if we go to the third energy level, then there's 3 sublevels in there. See, when n is equal to 1, there's 1 sublevel. When n is equal to 2, there's 2 sublevels, right? There's these 2 sublevels. When n is equal to 3, you can see there's actually 3 sublevels in there. And these 3 sublevels have L values of 0, 1, and 2. In other words, S, P, and D. And because they are coming from the 3rd energy level, you would have the number 3 in front of them for n is equal to 3. So 3S, 3P, and 3D. 3S, 3P, and 3D, 3 different energy levels. So to describe it as another example, for example, all of the orbitals of an atom with n is equal to 3 and L is equal to 1 would be collectively referred to as 3p orbitals, right? L is equal to 1, that's the p, and n is equal to 3. So 3p orbitals, or the 3p subshell. So, but really what we have to keep in mind then is that these orbitals aren't really just shells and rings with a fixed radius. Each of them actually has a shape and an orientation in 3-dimensional space. And s orbitals are more spherical in shape, and they become larger as n goes up. So an 1s orbital for n is equal to 1 would be a smaller orbital occupying, remaining closer to the nucleus. And as n gets larger, it occupies, or the electron has a probability of being farther away from the nucleus. This sphere, this spherical shaped electron cloud gets bigger, and the electron might be spending more time and more probability of it being farther away from the nucleus in a 3s orbital than in a 1s orbital. Are we okay so far?
Yeah.
Okay. So, and then p orbitals, again, these sublevels, again, aren't just spherical or shells that are an equal, a fixed radius from the nucleus. P orbitals have got actually a lobed shaped, almost like a dumbbell shaped with a node at the nucleus. So again, the probability of the electron being in the p orbital is it's being somewhere in this region. And because we can have 3 of them, the 3 of them are actually oriented in 3 different dimensions of the 3-dimensional axes. One you can describe as px, being in the x-axis. Another one can be described as py, running along in the py axis. And the 3rd p orbital would be along the pz axis. And then the d orbitals have this kind of a shape, and there's 5 of them, and they get a little bit more complex by the time you get to the 5th d orbital. And then the f orbitals are even a little bit more complex. But the main message here is that in the quantum mechanical model, we understand that the electrons aren't in a fixed radius like planets around the sun. They're not orbiting the nucleus in a fixed radius like planets around the sun. They are rather in electron clouds with a probability of being found in a certain location, in a certain orientation, occupying that electron cloud, having a certain shape in space.
Miss,
Okay.
I had
Yes.
a question.
Yes, Mark.
So could you just show me if for the chart where it was like if n equals like 1, only L equals 0 exists, and then if n equals 2,
Like this one?
yeah, or the other one,
This one? No.
no, the one after,
This
yeah.
one?
I think it's shapes and orientations of orbitals.
Shapes and orientations of orbitals.
Is, oh, no, it's not that one, that's not.
Okay. This one maybe?
Yeah.
Okay.
Yeah, this one.
Okay. Okay.
I just need to write this down.
So here, like, you can see, like, this was the very simplistic Bohr model where it thought that electrons would all be in the n is equal to 1, the electrons would be at this fixed distance, this fixed radius from the nucleus, and they would all be kind of orbiting on this path around the nucleus. And if the n is equal to 2, they would all be orbiting in this fixed distance around the nucleus. But now in the quantum mechanical model, we understand that there's all these sublevels, subshells, and that they each have their own shape and orientation. And when you have them all, they kind of give you this kind of a picture around the nucleus of electron distributions. And you don't think of, this is where I'm going to pinpoint this electron to be. Rather, it's a probability of finding an electron in that space. Okay.
Miss, I think I found the slide. It's 37.
Okay.
The second quantum number. Yeah, that one.
This one. Okay.
Yeah,
So the
this
second
is
quantum number, right? So then the second quantum number was discovered by another scientist. And when they took closer look at these energy level diagrams, they could see that actually each one of these principal quantum number energy levels, say n is equal to 1, and then n is equal to 2 and 3, was actually further split into 2 more lines. And at n is equal to 3, at this energy level, that was actually further split into 3 lines. So that led to the idea that there must be a second quantum number that helps to describe the energy levels of electrons around the nucleus. So if n is equal to 1, there's only one sublevel, so that's why you only see 1. And when n is equal to 1, L is equal to 0. And the relationship between n and L is that n has, or L has the value of 0 to n minus 1. So in this case, 0 to n minus 1, 1 minus 1 is 0. So you only have 0, one sublevel. When n is equal to 2, L can have a value of 0 and n minus 2. I'm sorry, n minus 1. So n minus 1 is 2 minus 1 is equal to 1. So L can have a value of 0 and 1. That's why there are 2 sublevels here. It's split into 2. So then at the third energy level, n is equal to 3, you get splitting into 3. And here L can have as energy values from 0 to n minus 1. So it can have 0, it could have 1, and it can have 2. And 2 is n minus 1. 3 minus 1 gives you 2. So these are the 3 values for L. Now it was becoming cumbersome to talk about n is equal to 3, L is equal to 0, 1, 2, 3. So instead, they adopted a naming system. So instead of calling L equal to 0, they gave it a letter. They started using a letter to describe this, and this became known as S. And when L was equal to 1, so when the secondary quantum number was equal to 1, they gave it a letter P. So they stopped using these numbers, and instead they adopted these letters corresponding to the value of L. Is that clear?
Yeah.
Okay. All right. So that's where the secondary quantum numbers came in. But they also discovered that in the presence of a magnetic field, there was actually further splitting. And the third quantum number was the magnetic quantum number. And they discovered that these, for example, the 1s and the 2p further split into more energy levels. So there was further splitting, and that they could see from the line spectrums. Where there was no magnetic field and where there was a magnetic field present, they could see more splitting. So that was discovered by Zeeman, and it's known as the Zeeman effect. And the effect was explained using this magnetic quantum number that describes the orientation of the orbital in space relative to the orbitals in to other orbitals in the atom, and the direction of the orientation x, y, z to the external magnetic field. So these are very, very complex areas of quantum mechanics. For our purposes, we are just going to understand how to arrive at the value of these quantum numbers. So for example, when L is equal to 1, there are 3 possible orbitals. So +1, 0, and -1. So that the value exists, the value of M subscript L has whole number values between -L and +L, including 0. That's where we get that when L is equal to 1, these are the values of L, -L, and 0. So it can have these 3 p orbitals. So, so for every value of n, there are n types of orbitals and n squared actual orbitals. So for the first energy level, 1 type of orbital exists, and then 1 squared orbital. So again, this arrives at 1. So for the second energy level, there's 2 types of orbital and 2 squared overall orbitals, excuse me. So 4 orbitals. What do I mean by that? Let's take a look at our table. What do I mean by at the second energy level, there's 2 types and 4 orbitals. And at the third energy level, there's 3 types and 9 orbitals. This is what I mean.
Wait, Miss, can I just take a picture of the last one?
Sure. So everybody, these slides are available for you to look at anytime you want. I've shared them with you, but yeah, go ahead. I'll.
Oh, okay.
Where was I?
It was the magnetic quantum number,
It was
39.
the magnetic quantum number there. That's where we were at. So any of so what do we mean by these? We mean
All right, thanks.
yeah, no worries. So here's in summary, you can see that at the first energy level, you have 1 type of orbital, right? 1 type. L is equal to 0, so it's a 1s, 1 type of orbital. At the second energy level, you have the L can have values of 0 and 1. So you can have two of these orbitals. You have 2 orbitals. So you have the 2s orbital and the 2p orbital. But overall, this makes up 4 actual orbitals. You have 1 of the 3s and 3 of the 2p. And this is as a result of this third quantum number, this magnetic quantum number. Because you can see for S, it can have the value of 0. So you would have just actually 1 orbital here. And here, this can have these 3 values. So you have these 3 orbitals here. Overall, 1, 2, and 3, 4. Altogether, 4. Now, how many electrons are in here? Where in each orbital can have 2 electrons of opposite spin, as determined by the 4th quantum number, the spin, the magnetic spin, the spin number. And it can, so electrons, 1 electron has to be in MS equals to +½ 1 electron is in the MS is equal to -½ In other words, spin up and spin down. And this way, each orbital can have 2 electrons of opposite spin. That's a term used for MS. And that's why actually at energy level is equal to 1, you have 1 sublevel and only 1 actual orbital. And in that orbital, you can have up to 2 electrons occupied. At the second energy level, you have 2 types of orbital. the S types of orbital, there's only one of them, and this can have up to 2 electrons. The p-type orbitals, you can have 3 of them. So these 3, again, each of these will have 2 electrons. So that's why your total number of electrons here in this sum of 4 orbitals will be 8 electrons. Let's take a look at the third energy level, n is equal to 3. L can have these 3 different values, and as such, we can designate them 3s, 3p, and 3d. Now, s orbitals, there's only one of them. They don't further split, but you can see the p orbitals, just like here, that the ml value for these p orbitals can be any one of these 3. So you could have 3 of them. And for the d orbital, because n is equal to 3, L is equal to 2, so the value of the ml can be these 5 numbers. So you can have 5 orbitals. All together, 1 plus 3 plus 5, there's 9 actual orbitals. And altogether, these 9 orbitals will have 18 electrons because each orbital will have the possibility of having 2 electrons of opposite spin. Okay?
So, Miss, is this saying like exactly how many electrons? Like, can you, using this, can you find out exactly how many electrons, or is it like an estimate?
No, this is these are the number of electrons that will occupy each energy level. And each
okay.
electron will have its own unique set of quantum numbers. For example, let's just look at the first energy level, n is equal to 1. N is equal to 1, there is only one type of orbital, and there's one of it, and it can occupy 2 electrons. So these 2 electrons will have different set of quantum numbers. One of them will have n is equal to 1, L is equal to 0, M is equal to 0, ML is equal to 0, and MS is equal to plus a half. The second electron will have the same for the first 3 sets, but the 4th quantum number will be minus a half for that one. So each one of these 2 electrons will have its own unique set of quantum numbers. And the same is true for each one of these. So each electron is uniquely described by these 4 quantum numbers. Now, when we talk about 1s, it's understood that we're talking about n is equal to 1 and L is equal to 0. That's a 1s orbital. 2s, it's understood that we're talking about n is equal to 2 and L is equal to 0. For 2p, it's understood that n is equal to 2 and L is equal to 1. That's a 2p orbital. There's 3 of them. And each of these occupies, can occupy 2 electrons. So 6 here, 2 here, 2 plus 6 gives us a total of 8 electrons in this n is equal to 2 energy level. Okay, so that's how many electrons are found at that energy level in that in these various orbitals that are designated by 2s, 2p, 3s, 3p, 3d, and so on and so forth. And just keep in mind that each of these orbitals has got a unique shape and a unique orientation in space, and the probability of finding the electron somewhere in this space described by these orbitals in these lobes. All right, so these energy level diagrams, here I just wanted to show you how for hydrogen or for other elements. In this side of the panel, I'm showing the case for hydrogen. And in this panel, I'm showing the case for other elements with many more electrons that can occupy many more different shells and sublevels. So in the case of hydrogen, as you can see, at any given energy level, at n is equal to 1, n is equal to 2, n is equal to 3, you only have all of these subshells that would be here would be at the same energy level. So here, for other types of atoms, at the second energy level, n is equal to 2, other atoms, these two sublevels will have different energies. So you would see them as two different energy levels. In hydrogen, they would just both exist at the same energy. The same for n is equal to 3. In hydrogen, these three, so 3s, 3p, and 3d, shown here in green. For other atoms, each of them has a unique energy level. In hydrogen, they're all at the same energy level. And we can see this situation that we're talking about here in, boom, here. So here is the energy level diagram for hydrogen. So you can see that the 2s and 2p are at the same energy level. They're not at different energy levels. The 3s, 3p, and 3d are all at the same energy level. They're not at different energy levels, which is what we see here actually this panel is another way of showing that. So here is the 1s in hydrogen and the 1s in a multi-electron type of atom. For hydrogen, the 2s and the 2p have the same energy level, but in multi-electron atoms, the 2s and the 2p are split. They have different energy levels. So the orbitals are generally lower energies in multi-electron atoms than in the hydrogen. And in higher number principal shells of multi-electron atoms, some of the subshells of different principal shells have almost nearly identical energy levels. So you can see here, the 3D and the 4S are almost the same energy level, for example. So that leads us to exploring the idea of what's the order in which electrons occupy these orbitals. And so for any given value of n, the sublevels then increase in energy in the order of S, P, D, and F. So for example, if we're looking at the second energy level, for n is equal to 2, we can see that the 2s has a lower energy level than the 2p's. That the 3s has a lower energy level than the 3p and a lower energy level than the 3d. Same with the fourth, 4s, 4p, and 4d is up here, and then 4f is way up here. So you can see that there's an increase in energy levels. Okay, so the energy diagram for an atom is directly related to its chemical properties and its position on the periodic table, because its position on the periodic table is related to how many protons it has, which is in turn related to how many electrons it has, which in turn dictates where those electrons are going to be. How many orbitals high are they going to go? Are they going to be at 2e? If there's more electrons than 2, well, then they start going into the 3p. If there's more electrons, then they start going into the d orbitals and the f orbitals. So it just depends how many electrons you have and sort of how many orbitals you're going to occupy. That will then dictate what type of bonds you're going to be able to form. So the rules for completing these energy level diagrams we went over in this off-bow diagram, which is just a memory tip for filling orbitals. You start by filling at the 1s and you continue to the 2s and then 2p and then 3s and then 3p and then 4s. So these are just indicative of the order which these come. So 4s comes and then 3d and then 4p. So because you can see that 4p is a higher energy than 3d. So that's why 4p comes after 3d. So if you follow along, you can fill in the energy level diagrams this way. And again, each orbital holds a maximum of 2 electrons, which we show with spin up and down notation here. Okay, so now we can go back to, okay, so how do these electron configurations, for example, for oxygen, for the element oxygen would have this kind of an electron configuration, because oxygen has a total of 8 electrons. It's element number 8 on the periodic table. It has 8 protons, so therefore 8 electrons. And these electrons, if you use that Aufbau diagram, you see that they start by filling the 1s orbital. 2 electrons can go in there. Once we've put 2 electrons in the 1s orbital, the next orbital available is the 2s orbital. 2 electrons go in there. And then you get to the 2p orbitals. The 2p orbitals, there's 3 of them, 1, 2, and 3. And following Hund's rules states that you have to put a single electron into each of the orbitals before you can start pairing them up. So if you fill up these 2p orbitals like this, that would be incorrect. This would be the correct way of filling them up, or this way. It doesn't really matter which way the arrow is pointing when they're on their own. What matters is that once they do pair up, that they have to be in opposite directions to represent the opposite spin of the electrons pairs that are in each orbital. Okay, so are we okay to this point?
Yeah, I can kind of like remember from last year.
Okay, good. All right, so
Kind of hard for me to understand while I'm in the class. I'll just study again and let you know if I have any.
okay, say that again, Shadisa.
I said it's sometimes hard for me to understand while I'm in the class, but I will study and let you know if I have any questions. I'm listening.
Yes, for
and,
sure.
Sometimes it's hard for me to understand.
Okay, but if you have any questions right now is a good time to ask, and I will just
Right now, I
explain
don't.
it again.
Fine.
You right now you're okay.
Yeah. Thank
Okay.
you.
Yeah. Everybody, don't hesitate. This is exactly what these review sessions are for, is so that you have had a chance to look at your lessons. And then now we get to review things that just need to be clarified again, things that you have questions on. Don't leave anything, don't pass anything that you have a question on, because in chemistry and all the subjects really, you're building on concepts that you've learned in previous lessons. So if you don't understand something, flag it down right away. Let's talk about it. Let's figure it out. Let's understand it so that then we can progress and move on and not fall behind. And then you will start feeling kind of overwhelmed with all the information. So then this is how you figure out, based on how many electrons an atom has, an atom like oxygen, or here in this example, we were looking at nitrogen, how many electrons it has, how many electrons it has. Electron is, nitrogen is element number 7. So it has 7 protons. Therefore, it must have also 7 electrons. So you start filling out the orbitals in order, and you realize that by the time you get to the 2p orbital, you have 3 electrons filling the 2p orbital, right? 1, 2, and 3. And you put each of them into a different orbital. You don't pair them up until these 3 each have got 1, okay? So which was the case when you go to the next element. Okay, so where are we? Then we got into chemical bonding, and we were going to take a look and see, okay, so these Lewis structures, and So here, for example, we can see that nitrogen has a total of 5 electrons in its outermost orbital. So if we go back to looking at what was the, actually it's right here. I can even blow this up bigger so that we can see. For example, nitrogen. Nitrogen, it would have 1s2 and then 2s2 and then 2p3. So in its outermost orbital, it would have it would have 2 in the 2s and 2 or 3 in the 2p. So it would have 5 electrons in its outermost orbital. So it would have a valence of 5 electrons. Fluorine, for example, would have a valence of 7 electrons over here, 2s2 and 2p5. Can everybody see that? Okay. And now there's a feature on the periodic table that actually makes it super handy. As it turns out, the group number 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, for the first 20 or so elements of the periodic table, which are the one we most commonly deal with right now, are actually correspond to the number of valence electrons. So right away, just by looking at the group number, which column they're in the first column, all of these have 1 electron in their outermost orbital, a valence of electron valence 1. For example, beryllium, magnesium, calcium, all of these belong to group 2. So they would have 2 valence electrons in their outermost orbital. Same with group 3, group 4, 5, 6, 7, and 8. In 8, you get the noble gases, the inert gases, and they have, other than helium that has 2, all of them have 8 electrons in their outermost shell. So they have a stable octet. So now you can see how the period number relates to principal quantum number, which relates to the number of electrons in their valence shell. That number of electrons in the valence shell, those are the electrons that are available for bonding. And so we started to talk about bonding, and right, we were at this stage. So now we're back to valence bond theory and the idea of 2 basic hydrogen atoms having each 1 electron, and in hydrogen, 1 electron is occupied in the 1s orbital, and this hydrogen has an electron in the 1s orbital. And as they approach, the 1s orbitals start to overlap until they're shared, and you form a covalent bond. And now each of these hydrogens has got a shared bond, and each of them is seeing 2 electrons now in its outer orbital. There's an overlap of their orbital, a sharing of their outermost orbital, and that forms that covalent bond. So let's look at another example. Instead of 2 hydrogens, now we're going to have a hydrogen and a chlorine atom. So hydrogen, again, would have 1 electron in its 1s orbital. And chlorine would have 1, 2, 3, 4, 5, 6, 7. And the 7 are distributed like so. Okay. And if you go back to, remember we were talking about electrons and how they relate to, where was it? How they relate to, oh goodness, where is that slide that I'm looking for? This one. Okay, so chlorine, as you can see, is part of group 7A, just like fluorine. And just like fluorine, it has 7 electrons in its outer shell. And we can see that also here by looking closely at its electron orbital number. So it has 3s2 and then 3p5. All right, so it has 7 electrons in its outer shell. Now, what can it do with its 7 electrons in its outer shell? Well, 2 of them are in the s orbital and 5 of them are in the p orbitals. So let's go take a look then at that example and see what's happening with the electrons, with those 7 electrons of chlorine. So 7 electrons of chlorine. You have 3s2, and then you have these 5 in the p orbitals. So here it is chlorine showing an example of one of its p orbitals, and you can have an overlap then of the 1s and the 3p orbital. So the 1s here is coming from the hydrogen, and this one lone electron here in the 3p orbital is now able to share and overlap with the 1s from the hydrogen. So they share and overlap and form a covalent bond between the chlorine, which you can see here. Here's the p orbital of the chlorine. And you can't really see the hydrogen nucleus because the hydrogen nucleus would be sort of at the center of this spherical 1s orbital here. And once they overlap and share, they form a covalent bond with each other. So the single 1s electron and the single electron in the p orbital. See here, you only have 5. This one is lone. So this lone one and this lone one share together, and then that way, hydrogen now has a complete set of 2 electrons in its orbital. So it's happy. And then now chlorine is sharing this electron from the hydrogen. So now it has a full set of 6 electrons here in its 3p orbital, and now it's happy. And they form a covalent bond, and this covalent bond will have a lower energy state than when each of these were in their individual atoms. And I encourage you to go back and watch these YouTube videos to see how are these orbitals overlapping and forming bonds. Now, when you have polyatomic molecules, for example, you have ammonia, which consists of like 1 nitrogen atom and 3 hydrogen atoms. So then you can write the valence electron diagram for nitrogen. And when you do for nitrogen, you see that it has 3 unpaired electrons in its p orbital. So each of these electrons can then share with the 1s electrons from 3 hydrogen atoms. So one of the hydrogens goes to this one of them goes to that one, the other one goes to here, and they start sharing. And once they share, they form 3 covalent bonds. And again, these covalent bonds now have a lower energy state than the individual atoms had, so it's very favorable. And just keep in mind that the bonding electrons have opposite spins now that they're shared together in a new bonding orbital. Okay, are we clear so far?
Yes.
Yes, okay.
Yeah.
Okay, so should I keep continuing with this? Should I keep going now to hybrid orbitals? Is that something we want to cover next?
Sure.
Yeah, do we want to continue that? Okay.
Yes.
Yeah, okay. All right, so then sometimes when you have overlap of these orbitals, they can change shape and form new kinds of orbitals called hybrid orbitals. And in hybridization, you have two or more orbitals coming together to create a new orbital. And this new orbital, what's important to realize is that this new orbital forms and then fulfills the geometry of whatever is the requirement of the system, whatever fits the molecule best. And when an atom hybridizes, it will restructure, it will redistribute its set of S and P atomic orbitals to form a new set of hybrid orbitals. And this hybridization is really driven by the need for the atoms to have specific geometric patterns. So let's just cover very quickly over here in this table. I've summarized what happens when you have an initial atomic orbital like S and P, or S and 2 Ps, or S and 3 Ps coming together, and how you change the orbital configuration to form a new set of hybridized orbitals. So for example, and then there's examples of molecules in which this situation happened, this hybridization happens. So for example, if you have a S orbital, that S orbital can redistribute by promoting one of its electrons to a higher energy level into its p orbital. And then in that case, you have hybridized sp orbitals. And the sp hybrid orbitals have a different energy level, and there's 2 of them, and they will have this linear 180-degree geometry, this kind of an orientation. And this is an example in beryllium hydride. You can watch this YouTube video, or if we like, we can watch it again. Or if you have an S2 orbital, and you have 1 electron in a p orbital, what can happen is that one of these electrons from the S2 orbital will get promoted, will get energized, and go to a higher energy orbital into one of these p orbitals. Then that way, now you have a distribution of electrons, whereas you had 2 in the s orbital, 1 in the p orbitals. Now you have 1 in the s and 2 in the p orbitals. So it becomes s, p, and p. Here we have s, P, and P. And these 3 now form a set of hybrids. They form 3 hybrid orbitals that will have a new geometry. And these are now called sp2 orbitals. So this will become this kind of an arrangement, and they will arrange themselves 120 degrees away from each other. And a good way to think of these is that if you had a pair of balloons and you were trying to tie them together, this is how they would orient themselves. This is how would be the geometric requirement for them to be tied together. It's kind of like that with the orbitals as well. Or if you had 3 balloons, so 3 sp2 orbitals, and you tried to tie these 3 balloons together, you would find that your 3 balloons will adopt a very similar geometry. Each of them will be 120 degrees away from each other, and they would all line in a flat planar fashion with 120 degrees angle in between them. So here in this case, you will have 3 sp2 orbitals forming. Here you had 2 sp orbitals forming. Finally, if you have a situation with 2 electrons in the s orbital and 2 electrons in a p orbital, you could get a promotion, an excitation of the s electron into the p orbital. And then you have a a hybridization and the formation of 4 sp3 orbitals. And these sp3 orbitals will arrange themselves in a tetrahedral fashion. So if you can imagine 4 balloons that you're trying to tie together at the tails, this is exactly how they're going to orient themselves. They're going to orient themselves in a tetrahedral fashion, maximally as wanting to be as far away from each other as possible, with an angle of 109.5 degrees between each of these orbitals. Okay, do you guys want to re-watch any of those YouTube videos? Is that something that might be useful at this point? Or are we okay?
I think I remember them. I'm okay.
Yeah, you're okay. Okay. Anybody would like to watch those videos again at this point?
I can watch them after.
You can watch them after. Exactly. All right. Thank you. So that was the idea of hybrid orbitals. So for sp hybridized orbitals, they come from the one electron from the s orbital becoming excited and getting promoted to a p orbital, and so on and so forth. Then let's talk about, so what's the situation in double and triple bonds? So what you have to remember is that orbitals can come and overlap to form covalent bonds in 2 possible orientations. They can either come head to head, if you remember, or they can approach each other side by side. So if they come end to end or head to head, you will form a sigma bond. The type of bond that will be formed is referred to as a sigma bond. If they are side by side, you would form a pi bond. Now, side by side doesn't make much sense for s orbitals. After all, they're spherical. What is side by side for s orbitals? Really, there's only one way you can bring 2 spheres together. But for p orbitals, if you can imagine them, they're like a set of dumbbells. There's 2 different ways you can bring them together. You can bring them together head to head and form sigma bonds, or you can bring them side by side and overlap and form pi bonds. So really, it's the way they overlap that signifies these 2 different types of bonds. So in a double bond, it consists of 1 sigma bond and 1 pi bond. So we can consider this molecule of ethene. Ethene is C2H4, and the 2 carbons are joined by a double bond. Here we have what's called partial hybridization, where we have 3 new sp2 orbitals and 1 quote unquote normal 2p orbital. And we've shown this now here in this figure, where you have these 3 sp2 orbitals, so 1, 2, and 3 around the carbon. And you also have 2 normal p orbitals around the carbon. So in your mind's eye, please try and overlap this picture onto this picture, where the carbons are overlapped with each other. So you have this and this in this partial hybridization. So in this partial hybridization, then, the sp2 orbitals, the pair that comes together head to head with each other, forms what kind of a bond? Who can tell me? These 2 that I'm pointing at, they're coming together in a head-to-head fashion. So in a head-to-head fashion, they form what type of bond? Sigma or pi? Anybody want to take a guess? All right, Shadissa, do you want to take a guess when you have 2 orbitals coming together end to end or head to head here? what type of bond will you form? A sigma bond or a pi bond?
Can I guess?
Yes, please. Thank you, Sasan.
I think pi bond.
So look at what the definitions are. When you come end to end, you form sigma bond. Side by side, you get pi bond. So this arrangement, you see where this is coming and the two ends are coming together. This is called end to end. So right here,
Okay.
this will be a sigma bond. Now a pi bond, now these two, look, they're arranged side by side. They're not coming head to head. They're not like, if you imagine what I mean by end to end or head to head, it's like they're almost like they're butting their heads together. That's where you get that sigma bond. But if they're coming side by side, they're just sliding like side by side, they're parallel in a way, you can see, yeah? This will form that pi bond that is shown here in this picture. This is that pi bond that's formed. So when they come head to head, sigma bond, here's another head to head where you have the s orbital and it's head to head with a p orbital. I mean, there's actually no other way an s and a p or an sp2 even can come together other than head to head. So this will be a sigma bond. It will be a single bond, sigma bond. That's that bond right there. All right. And here's another carbon hydrogen bond, covalent bond right there. Then here in between the two carbons, you have two things happening. You have one sigma bond forming, and because of the parallel side-by-side arrangement of these p orbitals here, you will also have a pi bond forming. And anytime you have a sigma and a pi, you have a double bond, which is the case right here. So here is that sigma bond, and here's the pi bond. And by pi bond, we really mean both of these clouds are the pi bond. So pi bond and sigma bond together form a double bond. And you can show, you can look at these videos to, specifically, you can look at the example of ethene at this.
Excuse me, miss, but first, like picture A, that has head to head too.
Yes.
No, it has, yeah. Why this is not a double bond? It has head to head and then end to end.
Head to head, it would be a sigma bond. If you want a double bond, it has to be a sigma bond plus a pi bond. That's why in between these two carbons, you have a double bond. Because what do we have between these two carbons? We have two things happening. We have a head to head, which is our sigma bond. So check, one sigma bond. And then because of the parallel arrangement of these p orbitals, we will also have a pi bond forming. So check, one sigma bond, one pi bond. Put these together, you will get this arrangement of pi and a sigma, hence a double bond.
Yeah, thank you.
Yeah, okay. So yeah, just remember, for a double bond, you need one sigma, one pi, and you will get your double bond. So triple bond. You can watch the example of the video to talk about the triple bond. In the triple bond, you need to have two pi bonds shown here in this figure. One pi bond and the second pi bond. And you have the sigma bond. So where is the sigma bond coming from? The sigma bond is coming from the head-to-head overlap of these sp orbitals here between the two carbons. So there's one sigma bond, check. And then you have p orbitals coming side by side in a parallel way, pointing the same way. And so you get one set of p orbitals. And then from the other ones, you get the second set of p orbitals. So whenever you have one sigma and two pi's, you get a triple bond. So a triple bond is one sigma and two pi's. Okay. What else can we talk about? All right, so do we want to talk a little bit about this valence shell electron pair repulsion model and how we can use this Vesper theory to predict what sort of a shape, what sort of a geometry, what sort of a shape a molecule is going to have?
Sure.
Sure, okay. So we can use this table to look at what kind of geometry a certain molecule might have. So let's just, before we do that, let's just review some of the assumptions, some of the underlying assumptions that go together with this Vesper method. So Vesper method is used to predict the shape of the molecule, and the shape of the molecule is very important to how it's going to react and how it's going to react with other molecules too, and how it's going to bond. So the atoms, one of the assumptions is that the atoms in the molecules are bound together by electron pairs. Well, we've been talking about how electron pairs coming together and forming bonds. That's how atoms are bound in a molecule, by sharing of electron pairs. So atoms in a molecule are bound together by electron pairs, and these pairs are called bonding pairs because they're involved in a bond. So you can have multiple bonds. You can have more than one set of bonding pairs of electrons binding any two atoms together. You could have multiple bonds, such as we talked about, such as the double bond, the triple bond. Those are the, oh goodness. We talked about the double bonds and triple bonds. So you can have multiple bonds between a set of atoms. You can have double bonds and triple bonds. Then some of the atoms in the molecule can have pairs of electrons that are not involved in bonding, and these are called lone pairs. For example, in the molecule of water, you have some lone pairs of electrons on the oxygen that are not involved in bonding with hydrogen. So then another important assumption in Vesper model is that the bonding pairs and the lone pairs around an atom position themselves in a way that their interaction is minimized. So again, think of that tying the balloons together. They're going to try and orient themselves in a way as far away from each other to be just in a favorable orientation. Electron pairs are negatively charged, so therefore they want to be as far apart from each other as possible. Okay, so if you think back to even hybrid orbitals and the way electrons occupy, it's the same kind of an idea. They want to be as far away from each other as possible. So lone pairs, though, occupy more space than bonding pairs. And I think, again, the logic there is also very reasonable because they're not involved in a share. They're lone pairs, so they're kind of taking up more space. They're not being shared. And double bonds occupy more space than a single bond. Again, that kind of maybe a way to help remember that is that if you think of it, well, a double bond is composed of more orbitals. There's like the sigma bond and the pi bond. There's, a pi bond and the sigma bond. So of course, a double bond is going to take up more space than a single bond, right? And also by that same logic, a triple bond will occupy more space because look how much space it's taking in this representation. So where are we? Okay, so those were like some of the assumptions about Vesper model. So now let's look at actually what this, for example, if we were asked to draw a certain molecule and we were given What's the shape of beryllium hydride? So you would start by drawing the Lewis structure, and the Lewis structure will show that the hydrogen will have one electron, and it will be bound to the one electron from beryllium by a single bond. And so if we consider beryllium to be the central atom, because it has two bonding pairs, it doesn't have any lone pairs, it would have the general formula AX2, right? The beryllium would be the A, and the hydrogens would be the X. So AX2, AX2. And you can kind of see this even from the formula, AX2, AX2. And AX2, if you look, will have a linear geometry because it has two bonding pairs. See, one pair, two pairs. It has no lone pairs of electrons. And so the geometry would be linear. And an example of this is this beryllium hydride, carbon dioxide, carbon sulfide. Those would all be linear types of molecules. If you look at beryllium fluoride, for example, it would have the general equation of AX3, right? The fluorine and the berylliums would be all bond together. You would have three bonding pairs. You won't have any lone electrons, and they would assume this trigonal planar shape. So think of three balloons tied together, each pointing as far away from each other as they can. So you would have this trigonal planar is what the geometry of this kind of thing is called. And also then, if you think of a molecule of methane, a carbon bound to 4 hydrogens, SCH4, it will have the general formula AX4, 4 bonding pairs, no lone pairs, and that adopts this, what's called a tetrahedral arrangement. Now, if you had a molecule of this sulfate ion, for example, you would look and see, okay, well, the central atom sulfur has got 6 valence electrons plus the 2 additional electrons because it has this -2 charge on it, totaling 8. So this gives, with the 4 oxygens, 4 bonding pairs and no lone pairs. So the general formula for this sulfate ion would also be AX4. So the sulfur would be here, the 4 oxygens would be like that, and they would adopt this tetrahedral arrangement. Did anybody try doing some of these Lewis structure Vesper theory predictions to predict the shape of any of these molecules? Did anybody try any of those? Were any of you having any difficulty with that? Did you try to do some of those?
I think I did them, I remember, but I don't think I had trouble.
You didn't have any trouble?
Yeah, I think so, yeah.
Okay, should we maybe just go through it to see if we can, okay, so let's look at, for example, CO2. Does anybody want to share with me what they found for CO2? So what kind of a geometry, and is it linear? Is it trigonal planar, tetrahedral, V-shaped, bent? Let's look at what this chart says here about what would CO2 be here. Actually, the answer is on the chart. Anybody? Borna?
Would it be V-shaped?
So CO2, it would have a carbon bound to 2 oxygens.
Oh, it would be linear. It would be linear.
It would be linear, yeah, because it would be the carbon bound to 2 oxygens. It won't have any lone pairs on it. The carbon would be the central atom, and it would be bound to 2 oxygens. And it would have a linear geometry. Actually, the answer is right here. CO2 is an example of a linear shape molecule like that. Okay, how about HCN, the second example here. Hydrogen cyanide. What would you predict for that? Based on Lewis structures and Vesper theory.
Linear.
Linear too, yes, exactly. It would also be linear. It would be an AX2. So how about BF3? This example, BF3.
Trigonal planar.
Trigonal planar. Very good, yes. And
These are all the forms that we have, like we not gonna get like something else. I mean, like, you know what am I talking about, right?
no, I'm not sure. Say that, say what you mean again.
So I mean, like all of the like shapes that we have are these. We have like nothing more, right?
This is pretty much the geometry, the shapes that you get. So all molecules, parts of them linked together are in this sort of an arrangement. If you can imagine, you might have something like this at one end, and then this might be another molecule that might have this kind of a thing. So you can imagine this might be plugged in there, forming the pyramid at this end. So yeah, it's all basically this type of arrangement around whatever atom you're considering, and then bound to some other atoms. If it's a small molecule like methane, this is all you get. But say it's part of a longer hydrocarbon chain, then you can imagine that maybe the rest of it might be a different geometry.
Yeah, but I mean, like, so A, B, and C were like easy. They were like literally the shapes were like in front of them. But about like D, S, I can see it. SCL4. What is that?
Yeah. Okay, let's go here. Yeah.
Yeah. Can we go over that?
Yeah, silicon chloride. So
Yes.
silicon chloride, you would have a silicon, and silicon is just like carbon if you look at the periodic table. Let me see if I can bring up a periodic table. Okay. So let me just. All right. So here's the element silicon, and it's right underneath carbon. It's in the 4A group, which means that carbon, silicon, and germanium, all of them will have 4 electrons, 4 valence electrons, 4 electrons in their outermost orbital, 4 electrons that are able to participate in bonding.
Can I take a guess? It's linear?
So take a guess. So you would have the silicon, and you can imagine with carbon, same as carbon. So it will have silicon in the center, and then it would have 4 chlorine atoms bound to it. So if you can think of even just looking at its formula, silicon and 4 chlorides.
Would it be tetrahedral?
So you would look down the list and you would see that, yes, it would be a tetrahedral. There would be your silicon.
Okay.
And there would be your 4 chlorines. Just like silicon hydride, for example, here.
Okay, thank you. Now it's clear.
Okay. Should we look at maybe another example? Yeah, let's go through all of the examples. So what else can we go through?
F, maybe?
So which one?
F?
F, okay. So F,
Trigonal planar.
F is a little bit different. So if you can think of your oxygen and it's bound to 2 chlorines. Now, how many electrons does oxygen have around it? Let's take a look at the periodic table just to refresh our memories. There. So it would have 6 electrons. And how many chlorines do we have to bind to it? We have 2 chlorines, right? 2 chlorines. So each of these chlorines right here has a total of 7 electrons. So it can take 1 more electron to become more like an inert gas, like a noble gas. So it has the capacity to take 1 more electron. Now, oxygen has got 6 electrons, and it can take it can share with 2 to become more like a noble gas. So if we think of how these are going to be arranged with respect to each other, it would be, can anybody guess? Can anybody sort of try thinking of what it might be like? So here we might have our oxygen. I'm going to try and do it on screen here and see how this goes. I don't think I've ever done this before, but okay. Maybe that can be our oxygen. Let's make this larger. Okay. So here we are doing our Lewis diagram. So 1, 2. Okay, so here we have 6 electrons. So, and what does the rule say? The rule says put 1, imagine like 4 sides to it, put 1 on each side, and then you can start pairing them up. Okay, so then you have your chlorine. And maybe I just want to copy this whole thing. And chlorine has got 7 electrons in it. So let's see, maybe we can arrange it like this and say, okay, so this chlorine, now we have 2 chlorines. So let's bring this over and whoops, let's grab the whole thing. Okay, boom, maybe you can see there. Okay, so there's 1 bond here, and let's just move that here just to make it easier for me to bring this over and say, okay, boom, there is that other bond there. So here we have oxygen. It has its now stable octet, 1, 2, 3, 4, 5, 6, 7, 8. Very happy. This chlorine also has 8. This chlorine also has 8. Okay, very nice. OCl2. Now, what do we have here? Here we have, what do we call these electrons that are not formed that are not bonding electrons? These are called, anybody want to remember what they're called? These are called lone pair electrons. Okay, so how many lone pairs do we have? Well, we have 1 pair here. We have 2, a second one over here. Okay, and our formula is AX2. So we might be looking at AX2, but wait, we have the lone pairs of electrons. We have how many lone pairs? We have 2 pairs of lone electrons, remember? 1, 2, 2 pairs, 2 lone pairs. So let's see, we have an AX2 plus lone pair electrons. So we have, this is actually our general formula. It's AX2 E2. So our molecule will have a V-shaped arrangement like this. And actually our answer is right there, OCl2, just like H2O is a V-shaped bent shape. And this V-shaped, this bent shape comes as a result of these lone pair electrons wanting to push these two farther away from themselves. Okay. So that was a good example to do. Did anybody have any questions about that one?
No, it makes sense.
Yeah.
No question.
Okay. So that's good there. So if you can think of these. Yeah, these are the lone pairs, and they tend to push things farther out and cause this sort of a V-shaped arrangement. So if you can imagine that oxygen is here, the chlorines are here, and then there's a pair of lone electrons here and a pair of lone electrons here, pushing things out. All right. So we have roughly 20 more minutes, 23 more minutes on our time. Where would you like to review now? We covered Vesper theory and bonding and orbitals and electron configurations to a certain extent. How should we spend the rest of this 20 minutes, guys? Let me know what other concepts you would like me to review.
Miss, can we do another example related to F?
Related to F?
Yeah.
Okay, so another example related to F would be water. Water would be a good example of related to F. So for water, it would be the same situation. Oops. Except, right. Except, so here we have our oxygen with the lone pairs. This would be hydrogen, right? Hydrogen doesn't have this many electrons. How many electrons does it have?
One.
One.
Valence.
Thank you.
Oh, and then the other two lone electron pairs, they make the 2 in the E2, so it becomes.
Exactly. It's the same situation. You get the AX2, but wait, you have two pairs of lone electrons. So it's more this AX2E2 geometry, which is the classic V-shaped arrangement of water. Okay. Okay, so we have 20 more minutes. Anybody else have a certain area that they would like us to review? So the bulk of that question spanned lessons 3 and 2. Any questions from lesson 4, which was intermolecular forces? Forces and bonds that are formed, not bonds, sorry, forces that are existing between molecules. And yes, bonds, sorry, yeah, you could have, we can call them bonds, as long as we remember that they are nowhere near the same kind of strength as covalent bonds, which are bonds within molecules. So bonds between molecules are orders of magnitude weaker than bonds within molecules. Okay. So here we talked about London dispersion forces, dipole-dipole, hydrogen bonding. And remember, these are not actual bonds, like they are in a sense of a covalent bond, but in this case, they're just more attractive forces. In the case of hydrogen bonding, because it's one of the stronger types of interactions, the term bonding is used, but it's not the same kind of sharing of electrons as we have in a covalent bond, for example. Okay, and keep in mind the three types of bond: London dispersion, which was the weakest one of the intermolecular bonds, and it arises from a very temporary, momentary, fleeting, instantaneous, almost as soon as it's made, it's gone, extremely short-lived dipoles that arise between atoms. Okay, so there is, as the electrons are moving about in their electron clouds and their probability density of the electron cloud, you may have a temporary dipole formed as a result of the electrons maybe being more on one side than the other, and that in turn induces a dipole in the other molecule. So that's where you get the London dispersion forces. And London dispersion forces are present for all molecules, whether they're polar or non-polar. London dispersion forces are present everywhere in all types of molecules. But if you have a polar molecule, you have, of course, London dispersion forces, but in addition to that, in a polar molecule, you will also have dipole-dipole forces. And these are attractive forces between, and they're stronger than London forces. And dipole-dipole forces are electrostatic interactions between ends of the molecules that have opposite charges. So if there is like a partially positive end, it will attract a partially negative end of a neighboring molecule and form a dipole-dipole force. And an example of a dipole-dipole force, a dipole-dipole interaction, we looked at some over here, where here you have attractive dipole-dipole forces in the solid state, and where everything is very neatly arranged in a crystalline format. But for example, in a liquid where the molecules are free to move, you do have some dipole-dipole forces, here shown in the red dots, but you also have repulsive forces in the blue. And overall, the net attraction is strong enough that the molecules remain in a liquid form and don't just float away into gas. Then we talked about hydrogen bonding, and hydrogen bonding being one of the strongest form of these intermolecular interactions. And how you can recognize whether there will be a hydrogen bond formation or not is that, first of all, you need to have a hydrogen, right? And then that hydrogen needs to be bound to one of these very electronegative atoms, such as the fluorine, the oxygen, the nitrogen. And this will then be attracted to this hydrogen that's bound to these very electronegative atoms of oxygen, fluorine, nitrogen. That hydrogen will form a hydrogen bond, an intermolecular bond, with the oxygen or fluorine or nitrogen's lone pair electron. Okay, that is where that hydrogen bonding is formed. That attraction is between hydrogen bound to one of these electronegative atoms. And I just want to refresh your memory about electronegativity. Trying to see if I can pull up this. This is from your Nelson chemistry book. Okay, so this table of increasing electronegativity, it shows that as you go down the periodic table, you get less electronegative. And as you go to the right in the periodic table, you become more electronegative. So you can see that those three elements that we talked about, those three atoms of nitrogen, oxygen, fluorine, are amongst some of the most electronegative members of the periodic table, NOF. Okay, so these three atoms, when they have a hydrogen bond bound to them, that hydrogen can then form a hydrogen bond with the lone pair of electrons on another neighboring molecule, or part of maybe the same molecule, as we talked about was the case in the very important molecules of proteins, the amino acid chains, where you have different hydrogen bonds forming either along the same chain or between different chains. But here you have, again, a hydrogen bound to a nitrogen, and it's able to form a hydrogen bond with the lone pair electrons of another oxygen, for example. Okay, everybody clear on how to recognize hydrogen bonding? This is very, very, very important to be able to recognize what situation you have when you have hydrogen bonding. Okay, actually, this is important enough that I would like to hear each one of you in your own words give me an explanation of, or teach me, when do you have hydrogen bonding? Who wants to go first? I will even bring up the slide.
Can I go first?
Yes, please, Hassan.
So I remember you said that hydrogen doesn't have like enough like electrons, or was it that?
So yeah, if you
A
look
lot
at
of electrons, yeah.
Yeah, so I can show you here this this table of electronegativity. It's right here. It's only the electronegativity of it is 2.1.
Yeah.
It's not as strong as some of these electrons, these elements here.
So it's like things on the left have like lower electrons, and then on the right they have more. So on the right top, like oxygen and like things around those seems like they have, no. Oh, yep, sorry.
Yeah, oxygen.
What was that one? Oh, God. What was F? Sorry.
F, fluorine.
Oh yeah, fluorine.
And
nitrogen.
Nitrogen, yes, and to a certain extent, even chlorine is there too. So these are the most electronegative. And what does electronegative mean? Electronegative means
they have more electrons.
It can pull electrons. It has a pull on electrons. It's hungry for electrons. It wants electrons.
Yeah.
And hydrogen will easily say, "Oh, here you go. You want my electron? Here you go. Take it," because I'm not very strongly electronegative. These are the more electronegative atoms here, up here in this top corner of the periodic table. N, O, and F are the ones that you really need to pay attention to. So, right, so when we have a hydrogen bound to and a fluorine, an oxygen, and a nitrogen, yes, go on. Go ahead, Susan, you can continue with what you were explaining.
Okay, sorry. So I said if there's like, because the oxygen wants the electrons, they're gonna get closer to them, each other connect, and then it's gonna steal hydrogen's electron like that.
Right, so that the electron, so the hydrogen then is able to form a hydrogen bond between itself and
the negative, non-binding electron pair.
yeah, so on a non-bonding electron pair. So here, do you see in this picture, this dotted line, red line represents the hydrogen bond between this hydrogen and then the non-binding electron pairs on a nearby electronegative atom or ion. Again, usually one of these three, F, O, N. So anytime you see that situation, as sort of all these examples here, hydrogen bonds, that's what you got, hydrogen bonds. Okay. So everybody feel like they're clear on that idea of where you get, what's the situation that hydrogen bonds arise?
Yeah.
Okay, perfect.
Yeah.
Very well. All right, what else? So all the different types of crystals and solids we talked about, ionic solids, metallic, all their different properties, crystals, covalent networks, quartz crystal versus glass, diamond versus graphite. It's all as a result of their intermolecular bonds. So if you remember in this covalent network crystal, we talked about where you have diamond and graphite. Both of them are made up of nothing but carbon atoms, but yet diamonds, very different property than graphite. Diamonds are extremely hard. Graphite along its planes is not very hard. It's and again, the strength of the diamond comes from its ability to form these 4 covalent bonds and form this crystal structure of 4 strong covalent bonds with 4 other atoms of carbon. Whereas in graphite, you only have covalent bonds with 3 other atoms. So so you have these sheets of carbon stacked on top of each other, and in between them, you have weaker bonds. Okay, these weaker London dispersion forces holding these layers together, but very different. And that's another reason why it has these non-bonded electrons that can move through the layers. And so graphite is a good conductor of electricity, whereas diamond, it's not. Its electrons are all tightly bound in covalent bonds. They're tightly shared between all of the other carbon atoms. All right. What else can we talk about in our remaining 5 minutes? If you can review this kind of slide on your own time and make sure you understand how we say that boiling point. So here is this BP value is the boiling point, how the boiling point increases with as the molecule becomes more polar, as it has a bigger dipole moment, and also as the molecule becomes larger so that it has more electrons as the electron number goes up. Okay. So as they, if the molecules have approximately the same mass and size, the intermolecular attractions increase with increased polarity. Okay. So this is an important slide. This shows an important concept of if you have more molecules that can form hydrogen bonds, you can have a higher boiling point. So these two molecules of acetic acid will have a higher boiling point, 391 Kelvin, than these two molecules of propanol, which will only have 370 Kelvin boiling point. They have the same molecular weight, both of them are 60, but acetic acid has a higher boiling point than propanol, simply because acetic acid is able to engage in more hydrogen bonds. What else? Well, yeah, I went through this slide with you just because I thought it was a very interesting example. I think this is from your textbook actually, but anyhow, if you just make sure you understand and you appreciate why these three molecules have a higher boiling point than their related molecules from the same group. Here you have group 6, for example, in the red, and all of them kind of follow this rule of just slowly, as their size increases, you get more, their boiling point gradually increases, but boom, here you have for when you have just hydrogen bound to oxygen, water has got a much higher boiling point. Hydrogen fluoride, much higher boiling point than any of its other molecules in the same group. Again, ammonia, much higher boiling point than its other molecules in the same group, almost as high as this one here. So just as you go along, just have an appreciation for what is the effect of hydrogen bonding here. I've highlighted this here in bold. Hydrogen bonding is the reason for these surprisingly high boiling points for these covalent hydride elements of these groups. Okay. What else? Yeah, make sure you guys have all understand polarity and unequal sharing between valence electrons, how you can use the difference in electronegativity to determine whether a molecule will form what type of bond, how electronegativity is very useful in predicting what type of bond is going to be formed between two pairs of electrons. Electronegativity is a value you can get from the periodic table or is sometimes tabulated like this. And so the difference between the electronegativities of two atoms can be used to determine what type of bond that's going to be formed. If the difference is 0.5 or less, you usually have a non-polar covalent bond, a covalent bond. If it's between 0.5 and 1.7, this difference in electronegativity between the two atoms, you have a polar covalent bond. And the character of this kind of a bond is covalent and ionic. Then you have purely ionic bonds when you have a difference of greater than 1.7, you have ionic bonds. And we went through this example of determining electronegativities of your first atom, your second atom, the difference between them, and then looking at the difference value, consulting the chart, and deciding what type of bond you're going to have, whether it's going to be ionic, covalent, or polar covalent. And once again, this is the trend in electronegativity. Okay, it tends to increase as you go down this way. The most electronegative elements are in this corner, and the least are in this corner. And you can look up their values and determine the difference between their electronegativity and figure out what kind of bonds they may engage in. Okay, We talked about how to write these Lewis structures for ionic bonding pairs, how to use Lewis structures to show between when you should have more than one type of bond. It's not just 2 atoms, but it's 3, but binding to 2, and what kind of a Lewis diagram that will form, how to write that up. We went through that. You can also review it yourselves again. Anyways, we are at the end of our time. If you have any further questions, please send me an email and we can help you. I can help you by email, or we can talk about it before class or after class next time. Okay, the next unit we are going to be talking about is the, let's see, there we go. So unit 2 starts Wednesday with lesson 5 on hydrocarbons. Then we're going to be talking about functional groups, types of organic reactions. And then I wanted to talk to you about lesson 8. Lesson 8 is going to be an independent study unit, means that you can study this on your own. You will look at my slides and you will study this on your own. And then the key questions for this independent study unit will be treated as a bonus. And just to clarify what I mean by a bonus, it's due on Sunday, October the 17th. If you choose to hand it in, and because it's a bonus, it's optional. You don't have to hand it in, but if you do hand it in, at the end of our semester, if you have handed in bonus questions, say you've handed it in all of your assignments plus the bonus questions, then I can use these bonus questions to drop your lowest marks for your assignments for as many bonus questions as if you've handed in.
Oh my God, sorry, miss. If we email our assignments to, does it count, or we have to like put it in the Dropbox? What's that?
Okay, so I noticed that, yeah, some of you still have emailed it to me. I really prefer that you put it in the Dropbox, because then I can just go to the Dropbox and grab everybody's assignment in one shot, rather than having to search through my email and finding those emails that came with assignments. So it would be really great if you could use that Dropbox that I've provided for you. I sent you an email with all the links to the Dropbox for the different lessons. So moving forward in unit number 2, please, everybody deposit your assignments into the Dropbox, and please make sure that you name your assignment with your name and key question. So it should say Shadissa, key question, 5.
Okay, but from now on I will, but
yeah, perfect. Okay.
Sure.
Yeah, that's fine. So moving forward, that would really help me a lot if your assignment was named the right way, so that when I get it all, I don't have to deal with, oh, this one just says document, or this one just says, answers. It has your name on it, and it clearly says key question 5, key question 6, and so on and so forth. So yeah, on Wednesday, we are going to cover hydrocarbons, and the key questions for that is due Sunday, October 3rd. You only have one assignment to hand it in this weekend. It just worked out that way. So that's nice. You can use the extra time to review and study. Okay. All right, everybody. Have a wonderful evening.
You too, miss. Bye-bye.
Have a good
night,
night.
miss.
Bye-bye.
Bye.
Exacto.